All right, welcome back. So here we are. We're in the first lecture for Module 10. Module 10, we're going to dive into deep learning. And this is just an intro into deep learning. Now, we've alluded to a lot of aspects of deep learning. We've talked about it in different ways in the three different modules associated with machine learning. But now we're actually going to get into it and do it. So in this module, I've got the last assignment is become available, and got a video in this series of lectures. The second video will be an intro to the deep learning assignment notebook. So what we're going to talk about now is a lot of stuff leading up to that. We'll talk about some of the code between this lecture and what will eventually be the third lecture in this series for Module 10. So let's deal with the deep learning revolution. So let's start with the key idea that deep learning is at the core of the latest developments in AI. What we're doing with generative AI and everything else, it's founded off of deep learning. All right. So at this point, we've got an understanding of what AI is. It's a very broad term. I always compare these concepts to those Russian nested dolls. So this one encompasses machine learning. So machine learning is a subset of AI. Just because something is AI doesn't mean it's machine learning, but if something's machine learning, it is AI. The same follows suit when we look at the relationship between machine learning and deep learning. Everything deep learning is machine learning. Only some of the machine learning is deep learning. And we can see the progression over time. So the last 10, 15 years, deep learning has strengthened and become very popular. For about 30 years leading up to that, we had machine learning and being able to identify what's spam or junk email. And we had computers that were beating people in checkers and chess, and a variety of other games leading up to that. So let's start with another key idea. There's a lot of hype around deep learning. So what do you mean hype? We hear it all the time. Somebody talking about AI, and all too often they don't really understand what AI is or how it works, but they know they're being impacted by it on a daily basis, and they have to get an understanding of what it is, and they think they know, and all too often they don't really know. So Gartner has a technology or information systems hype cycle that it publishes pretty much every year. And this hype cycle starts out where, man, technology enables it, expectations shoot up, we become disillusioned because we realize it didn't do what we wanted it to do. So we call this the trough of disillusionment. Disillusionment. Oh my goodness, I'm getting caught up on that. Disillusionment. At that point, we start to realize the things that it was able to do, and it slips up a little bit, and now we are utilizing it to get stuff done for us. Now it's not just AI when we're talking about this. Here's one from 2017. And when we look at it, we say, all right, what do we got going on? We see machine learning in here. I see deep learning. I don't see AI in there so much. I see augmented data discovery, brain-computer interface, human augmentation, 5G. So there's all these things, and we see where they are in the hype cycle. I want to say the life cycle. It's the hype cycle. So here's that peak. Deep learning was in the peak. That's just about 7 years ago now. Now we jump ahead 2 years. Deep learning is starting to slip down into that trough of disillusionment, but it hadn't gotten there yet. And we can go to Gartner and see where are things today, and they eventually work their way down and come back up. So we see speech recognition here Man, it's getting adopted everywhere. We come back over here, I don't even see it. It's been around for quite a while at this point, but it wasn't that big a deal. So here we see it's coming back, and it's everywhere now. Computer vision, we see it. So this is 5 years ago, and it's changed from then. So what's the next key idea? Deep learning has revolutionized computer vision. You say, well, wait a minute, what's computer vision? Well, computer vision is having, let me back up. Computer vision, let's look at it as dealing with images. The computer actually seeing something or interpreting an image. Now, it could be a static image or video images, which are static images sewn together. So a computer can interpret these images. Now, we're not just interpreting images, but we can make predictions based on images. This is something that's been a long time coming. The only way we're able to do it is because of the capacity of computing, the evolution of CPUs and GPUs. So with that said, we've got a lot of data that we have available to us to play with. And we notice that when we look at our TVs, our computer monitors, the resolution is getting so much better. Camera's resolution is getting so much better. But when we look at images, a lot of times, man, these are really bad images, low-res images. And if we had to look at a data set, oftentimes the data set is a combination of horrible image, black and white, grayscale, and color images of varying degrees of pixelation and high resolution, low resolution, etc. So deep learning has allowed us to do so much with these images, but we still got limitations. So this computer vision is our ability to utilize a computer to identify objects in images. That's where we say computer vision. The computer sees the image. So a camera sees pixels. Now let's assume this is grayscale. It's 2 dimensions, one axis this way, the other axis going this way, of pixels. And each pixel has a value from 0 to 254. There's 255 different combinations that vary from white to black. Let's say that's grayscale. So it's a 2-dimensional piece of data that we're looking at. If we were looking at this in color, it would be 3 dimensions. The 2 that we see for each pixel's width and height, and instead of being 1 dimension, 0 to 254 for grayscale, we have 0 to 254 for R, 0 to 254 for G, and 0 to 254 for B. We've got the RGB layers that make up the color schema that we're using. So by having a 3-dimensional matrix, we can visualize or digitize an image into numbers. Now once we got into the numbers, the computer sees this, and this would just be 1 layer if we were talking about RGB. If we were, no telling what layer it is, or this could be 0 to 254 relative to this being grayscale. So now, how's this all work? Well, we're looking at things, the difference between machine learning and deep learning. We've got these images that we feed into a model, and we manually extract features from the image. So essentially what that means is this is like supervised learning. We're telling the model what features exist. We run it into machine learning, and then it will classify whatever the image is, car, truck, bike, whatever. Now, if we look at this from the deep learning perspective, we take all these images, we feed it into the model, and the model tells us all the different things that exist, and then we can go put labels on each one of them as they are classified. Or it'll find different features that are important within there to make it a truck, car, bicycle, depending on how we configure the network. So we've got different models that we can use. They're already preset, if you will. And then we just reuse them and modify them as needed. And ImageNet, it's a database of images. It's got a total of 1,000 object classes, 1.2 million in the training set and 100,000 in the test set. So we've got this ImageNet database, and then from there we're able to use ImageNet, and it's grown immensely over time. We're able to use it to apply these different models to identify what those objects are, to classify the objects. So deep learning may refer to a wide variety of neural network architectures. We talk about neural networks. Deep networks are neural networks, and they have the following properties. They got more neurons than just a normal neural network. They're more complex ways of connecting the layers. So in neural networks, we have multiple layers that the machine learning goes through. But when we're talking about deep networks, deep learning, it's not just a couple of layers. We've got a large number of varied types of layers. And we could start out with things, let's say we start out with something that's 700 some odd features that are being fed into it. The different layers could break that up to where we're over 1 million features, only to bring it back down and classify it into one of 2 or one of 10 categories or classes. So that's how these networks will work. It's very complex in how it works. The amount of computing power available to us has allowed us to train massive data sets to where they really learn a lot now. And we can have it automatically learn different features that otherwise we wouldn't necessarily see them. So we look at artificial neural networks. We've got perceptrons. We feed in 2 different input cells, and then we end up with 1 output. Feed forward, 2 inputs go to 2 different hidden cells, which end up both feeding into 1 output. So this input will feed there and feed there. This one will feed there and here. And then each of those will result and feed into the output. And there we go. Conceptually very similar to radio-based. We've got deep feed forward. So each one of these inputs feeds each one of these hidden cells, which feeds each one of the ones that follow, which all 4 feed each of the 2 outputs. So these can get very, very complex, and when we look at what's going on, some of these are going back and forth. There's a variety of different types of variants and architectures here. Okay, so We're not going to deal with all of these. We're just going to look at the different concepts, how they work, and then you're going to go explore. Do some trial and error with different examples that we provide you. So deep learning is a multi-stage way to learn data representations. Okay, it's a multi-stage. For our purposes, deep learning is a mathematical framework for learning representations from data, because everything we're doing is converting an image, in many cases, into numbers. We took our data, we wanted it all to be numeric so we could perform mathematical calculations, statistical probabilities, and everything else. But more specifically, deep learning, as we said, is a multi-stage way of how to learn data representations. It's pretty simple, but it turns out sometimes things that are very simple, sufficiently scaled, can end up looking like magic. It's like, how were you able to do that? And traditionally, they're pretty simple to use. They may not be simple to build out at the deep programmatic level, because a lot of these, we're looking at complex calculus to be able to do what we're doing, but that doesn't mean that I've got to know calculus to be able to do deep learning. So we start out with an image. That's our original input. It'll go through a layer, which feeds into another layer, which modifies it, feeds it into another layer, modifies it, feeds it in another layer, and then we end up going through the output. And we may have to do some polishing up in these last little steps here, flatten, whatever we may have to do, to get it where it needs to be for the clean formal out or final output. But ultimately, it will classify it 0 to 9. Oh, that's 4. So if we look at it in this a rough way of looking at it, we got the 4. We break it up into its components. So layer 1 breaks it up. We take those outputs, we feed them into the next layer. And like I said, this could go from one in, let's say 28 by 28, it feeds in, and now we'll end up with a variety of different outputs that come out. And we could have 20,000 coming out. That feeds in here. This could feed out or output 1.2 million, which feeds in here, and that just digs even deeper. So we're getting down into pixels, pieces of pixels, only to feed it into that final layer and it to say, yeah, that's a 4. So how it goes about it, we've got these transformative layers and ways to polish things up in between these convolutional layers that we're dealing with. All right. So we look at it, how's this all work? Everything's based on weights. Input comes in, and we've got weights associated with this layer in the transformation. Pass it over here, there's weights associated with it. And then we come up with a prediction. Now these weights, we can determine what they are, we can let the system determine what they are. And essentially it's finding out what's important at each of the different layers, so that ultimately the predictions come out what we want them to be. So if we look at as a loss function, comes in, weights, comes down to the next one's weighted. We got our prediction. Prediction's what the model thinks it is. Target is what it actually is. That difference becomes our loss function. We've got a loss score. Now, we've dealt with that in depth in the last 3 modules. All right. And we've got the same thing here. But what ends up happening is we come up with that loss function. It develops a loss score. That loss score feeds back to the optimizer, which modifies the weights, and it cycles back again to see, hey, did we do better this time? So depending on what this value is, it'll feed back, and the thing starts learning from it's almost like a trial and error kind of scenario to where the system runs through and it says, well, where were you? What's this number? Oh, all right. What can we change to try to do better? And in the past, we've gone in and dealt with changing hyperparameters, and in this last assignment, we'll deal with changing hyperparameters. This model may go through and change the things on its own to modify the weights so that it has a lower loss. Okay, so when it comes to training it, we're going to go through and feed the data in batches. And those batches will go through epochs, and ultimately it'll back propagate, we'll change the weights, go back, do it again, go back, do it again. So each of the epochs, it will go back and say, all right, let's try this. Oh, let's try this. And as we go through and do it, and you'll see it in the second video, and in the notebook for that final assignment, you'll see where I've already run it, or you can go run it. And keep in mind, these deep neural networks, they take a while. It's not something you're just going to hit a button and it'll be done in a minute. There's sometimes you may wait half hour, an hour, a few hours, depending on how much data and how big the data is. And when I said that we're breaking it from, say, 28 by 28, that's 700 some odd different items being fed in. Next thing you know, you're up to over 1 million. That's a lot of transactions that are taking place to get you through one epoch and another epoch. Okay, so we've got to go through, we've got to train it. It may take a while, but you will see as it's learning, it'll output the data, it'll output the results, and you see that it's getting better. It's getting better. It's getting better. It's not about so much where it is between point A and the end. It's, hey, where do we end up? How good could you get? If we did it, kept doing it, instead of 100 epochs, if we did it for 400 epochs, would that help? You know, there's times, and we've all seen it, there's times where, yeah, if I spent more time, could you do any better? No. It's like lifting weights. If I said, all right, here we are, here's the bar, here's 400 pounds. Can you lift this up? No. Well, how about if I give you 20 minutes? If I give you an extra 20 minutes, would you be able to lift that 400 pounds? Yeah, no, it ain't going to happen. So sometimes adding more time or more epochs is not going to help. Other times it may help depending on what we're talking about. So we could have what we call mini batches. So we'll run little simple mini batches through. It'll do its thing, forward propagate, calculate a cost. We'll use descend gradient of C, adjust the weight, and next thing you know, we end up with a better prediction. So we go through this training just to get better. So we say back propagation. That's huge. It's our way of learning through back and forth. Here, let's do this. Push it forward. You like what we got? No, try it again. And when it comes back, they make an adjustment. When I say they, the neural network makes it, or the neurons makes an adjustment, sends it back again. So we've got this back and forth. What it learns, it tells the previous neuron, which makes the adjustments and tries, how's this? Is this better? Now, there are times that we could use, and I think, if I recall, this is coming from MATLAB, where we can go through and visualize data using their software. It's not something I've got access to right now, but we can go through and we can use Google Colab, and we can kind of see what we're doing in there, and you'll see when it comes to the dashboard what we're able to see. It just gets better and better. So we've got our data. We look at the ratios. We send the features in. According to this, we got 2 features going in. There's a hidden layer. We hit that hidden layer. It does its thing, and then it spits out. we could go in and add more layers in here, modify the layers, and so there's utilities that will allow us to test things and see what works. All right. Pretty dashboards. Here it got really convoluted. We've got 4 different hidden layers, and then there's our output. 2 feed-ins, 8 neurons that it's going into, 8 following, then we've got 4, and then we've got 2 that go into our output. Okay. So we've got, where are we at? We're about 32. So we've got TensorFlow. And there we go. That's the TensorFlow front end. I've forgotten. It's been a while since I created this. And so we can go use TensorFlow, their playground, to go in and modify things. I want to add a neuron, take a neuron away, add another layer, add more, and how's it playing out. And we can see each time we change it, the changes in the result when it comes to how it's classified, the shading in the background and how it classifies things. So we've got a link in the PDF where you can go play with that and see how things play out. So we've got artificial neural networks, and we've talked about them. And we've got these fundamentals and different examples of it. So we lay things out. So artificial neural network is supposed to be just like a human brain. It's more than the perceptron. It's got tensors, layers, loss functions, optimizers, so much back and forth. We look at how neural networks learn. We've got improving the way that neural networks learn, and we'll deal with MNIST classification using Keras. So let's look at the inspiration relative to the human brain. So we've got a neuron. We've got this cell, and it's got an output. So this cell has triggers that tell it stuff, and then we've got the outputs. So our neurons need to work similarly to what's going on there. So we've got a perceptron. So what we see, that's our inputs that feed into the neuron. That neuron then processes it and output. Now, many times you'll see this called an agent. So we will have some input fed into the agent, and then the agent will have an output, and that output then does something. It could trigger an actuator or something like that. It's almost like, oh, I smell smoke. Get out of the house. Input, the smell of smoke. Neuron processes that input. So perceptron takes it, perceives what's coming in, processes it, and says, here's what we got to do. It could be an audible, it could be something actually happening, like I said, get out of the house, whatever it may be. So when we look at this math-wise, we're looking at inputs, the perceptron, and an output. We're not going to dig deep into the math terminology on this because I don't want to scare everybody and make you think, oh, I'm not great at math and I just can't do this. This is a 2-year program and you do not have to have calculus. Now, if you wanted to boost your math and keep digging deeper into everything, that's a great idea. The further through your program that you go, the higher level we're going to be. For the bachelor's level, you're likely to have to start getting into levels of calculus. The 2-year level, we're not having to. So we're just going to try to keep it as simple as we can. We've got the perceptron. The positive weight represents an excitatory connection and a negative weight, which is an inhibitory, meaning positive weight, yay. Negative weight, boo. That's all it is. The perceptron output says, all right, here's the weight, and then it just processes everything to say, are we dealing with something good or bad? Okay. So here's an equation that's commonly used. The deeper we get into deep learning, oh, this makes sense. But there's our equation for deep learning. So when it comes to perceptrons, we've got these different layers. Oftentimes we call them hidden layers because this doesn't see what's happening. They just see the ones they're talking to. So beyond the perceptron, we've got what are called sigmoid neurons. And they're similar to perceptrons, but they're modified so that small changes in their weights and biases can cause only a small change in their output. Now, that can be a really good thing. We don't want these neurons, whether it's the ones we just looked at or sigmoids, to be overreacting. So this is just saying that I've got a neuron that's a little more subtle. Okay. So essentially we can break things down. We've got the inputs, we've got the connections from the inputs to the neuron, and then we've got the output. Now we've got an activation function in between that says here's what's going to take place here to get where we got to be. But essentially that's it. We've got these dendrites which have weights associated with what's going on, the importance of each thing coming in. I don't want to overwhelm you guys with this, I really don't. But this is probably one of the most complex modules that we're dealing with, but I don't have a ton of this in the assignment itself. The assignment itself is not bad. So when we look at this, we go, oh man, he's going to hit me with Tang and sigmoid, ReLU, and all this stuff. That's not what you're going to see in the assignment itself. So when you get to that next video, you'll see it. It'll make a whole lot more sense. So we're going to deal with tensors, layers, loss functions, and optimizers. So we looked at it. We've got the input. It comes into a layer. That transforms the data based on some weights. Comes down to the next layer, transforms the data based on weights. We come up with a prediction. Goes against what should be true. We got our loss function, and that gives us a loss score. Feed that back to the optimizer. It looks so much familiar to what we looked at before. We're just getting a little more detailed in that this is data transformation. Okay, so there's our model, a rough sketch of it. So representations. So what's a tensor? Tensors are generalizations of vectors and matrices. So let's take a step back. What's a vector and what's a matrix? A vector is sequential data. An array is a vector. A list is a vector. But for the context of what we're dealing with in data science, everything that traditionally is in that vector, it doesn't have to be, but traditionally it's all going to be a given data type. So if we look at a feature, which is a column, they have to be all the same data type. Vectors can be a single row with multiple features. Well, it doesn't mean a whole lot if we look at it that way. So vectors, we'll look at that as an array, one dimension, and that vector is traditionally going to be all the same data type. Matrices are 2D. And then we get to tensors, which is a 3D, let's say matrix, they want matrices to be like a spreadsheet, and tensors are three-dimensional structures. Okay. We don't see tensors used as much outside of data science. We just say three-dimensional matrix or matrices. Are we limited to 3 dimensions? No. It could be n dimensions, which becomes very complex when we're trying to visualize it or come up with some kind of, what would that look like? These would look like a train of train cars. These would look like a checkerboard. These would look like a Rubik's Cube until we get higher than 3 dimensions, and then it becomes abstract. It's difficult to have a visual representation of it. So go through and we look at different examples of tensors. Videos 5D, images are 4D. We've got time series 3D, vector data is 2D. A 4D image data tensor. It's complex. So we've got 2 dimensions here. Each color channel is another layer. So we say, well, that's an image. Yep, that's an image. And here's another image, and here's another image. That's 4D. Here's 3D, and then we've got another dimension is the other layers that make up that tensor. Okay. So when we look at things, it all breaks down into X and Y's. It's like we're using Legos to build the different layers of deep learning. Each of the layers have to be compatible with the one that precedes it and the ones that follow it. Okay. So we've got the input layer, we may have one hidden layer and then an output layer. Or we could have multiple hidden layers. The difference between neural network and deep neural network is neural network, look how shallow this is. Deep neural network, and nothing shallow about this. It starts getting ugly. And we'll look more in the following videos at different examples, and we looked at some previously. So when we're talking about loss functions and optimizers, go ahead and cover this, and then we'll snip this lecture into an end, and then pick up the back half of this slide deck in a second, or which would actually be the third lecture for Module 10. So once we've got this architecture laid out, how we want the neural network to be laid out, all the different layers, then we've got to determine what loss function we're going to use, the objective. That's what looks to see how those weights are calculated to backpropagate, to send that data back to help it learn moving forward again. What optimizer? SGD, Atom, what are we using? Got a variety of different optimizers we can use. What is going to be our loss function? Now, if I'm doing a 2-class classification problem, I may want to use binary cross entropy. Bunch of classes, categorical cross entropy. If it's a regression problem, let's try mean squared error. So each one of these is a different loss function to calculate what the loss score is to backfeed for the weight. Right. So we've got a variety of different ones. So let's go ahead and lob this one here, and see you back in lecture 3 for Module 10, where we should be wrapping up deep neural networks.